In this video, we're going to talk about magnetic force. And more specifically, we'll be talking about the magnetic force on a current carrying conductor placed within a uniform magnetic field. So consider now a wire as such carrying a current I placed in a magnetic field of flux density B. The formula goes like this: the magnetic force on this wire FB equals to B perpendicular IL. Now, the most important thing over here is this B perpendicular here. And what that actually means is we only want the component of B. Let me write that down. The component of B perpendicular to your current. And so how do we do that? And so we need to resolve this flux density vector into the components which are parallel to this current and perpendicular to it. Okay, let me try to draw that again so it's a little bit nicer. Okay, and so you can see quite clearly, if I take this as my B vector, then that over here will be B parallel, and this over here will be B perpendicular. And so it is the case where only this component of the magnetic field contributes to the magnetic force. And so, for example, if I am given this angle here, theta, then we can say that FB, or let me work this out first. So this would be B cosine theta, this would be B sine theta, right? And so we can say, of course, FB equals to B IL sine theta. Okay, so of course, depending on the angle that they give you, right? So if I had, let's say, given you this angle instead phi, then of course the magnetic force would be BIL times cosine phi. And so if we think about it, let's take this down a little bit over here. Okay, if I have a magnetic field that goes like this, right? A wire that is placed parallel to this magnetic field so that the current is parallel to the magnetic field will of course experience a force of 0, right? Because there is no component of the magnetic field that is perpendicular to this wire. And as this wire rotates, okay, the perpendicular component of the magnetic field gets stronger, and of course it gets the largest it can possibly be if the wire is perpendicular to B, in which case FB will simply equal to BIL. The entire magnetic field is perpendicular to the current. Now, magnetic force, of course, is a vector, and so the direction is determined using Fleming's left-hand rule. Okay, and so let's talk a little bit about Fleming's left-hand rule and what it represents. So we have here, of course, the thumb. Okay, the thumb should always point in the direction of the magnetic force. The second finger will point in the direction of the magnetic field, and the third finger should point in the current direction of I. Well, actually, more specifically, the second finger can point in the direction of the perpendicular component of the magnetic field. And so for this example over here, we can do a simple practice. Okay, your third finger should point in this direction. Your second finger should point in this direction, and you'll find that your thumb will point into the screen, and so the force is in fact acting inwards, and so you expect this entire wire to be shifted into the screen as according to Fleming's left hand rule.